This is lesson 6.2 on multiplying and dividing radicals. We'll go ahead and get that heading in our notebooks. The first thing we're going to talk about is how to tell if a radical is completely simplified. So a radical is completely simplified if the following conditions are met. First and foremost, if all of the possible factors have been taken out of the radicand. Remember, the radicand is the number inside the root symbol. So if we've broken it up and taken out everything that's possible to remove from the radicand, then the inside is considered completely simplified. And we have one last condition that has to be satisfied before we can consider it completely simplified, and that's that we are not allowed to have any radicals in the denominator. We call this a rationalized expression. So if we have an equation with a square root in the denominator, for example, we would have to get that square root out of the denominator before we could consider this rationalized or simplified. So we already know how to remove factors from expressions. We will talk about how to rationalize expressions. But first, I want to talk about how to combine radical expressions, because that will help our simplification process. So let's go ahead and look at combining radical expressions. And we're going to start with combining products. Remember, product means multiplication. So in this situation, all I'm doing is multiplying two radical expressions together. So we're going to look at a standard form of this. If I have two radical expressions being multiplied together, we could see one of them could be the nth root of a. So any radicand to any index. And let's say I'm multiplying that by the nth root of b. In this situation, we have the same index. That's really important. As long as that letter n is the same letter for my root of a and my root of b, so the same root, the second root or the third root or both the fourth root, as long as that's the same, I can combine these two radicals under the same radical sign. So that would be the nth root of a times b. So they end up living together under the same radical symbol. So if we have the same index, we can multiply the radicands. All right. So let's take a look at a very quick example of that. Let's say I have the fourth root of 3 times the fourth root of 5. Since these two roots are both the fourth root, they have the same index 4, I can combine them under one radical. I can have the fourth root of my radicands multiplied, 3 times 5. Once we do that, all we have to do is simplify, which means actually multiply these things together and see if we can remove anything from my radical. If we simplify this, we end up with the fourth root of the number 15. The only factors of 15 are 3 and 5, and they don't repeat 4 times, so nothing can be removed from this radical, so this would be my final answer. Great. That's all there is to multiplying. We just multiply what's underneath the radical sign. Let's go ahead and take a look at quotients. Quotients, remember, a quotient is the product of division, so if we have two radicals being divided, we're going to see a similar pattern. In this situation, let's say I have, again, the nth root of a, but this time I'm dividing it by the nth root of b. Now again, we have to have the same index in both of these, and as long as the n is the same number, so the third root, the fourth root, the 17th root, it doesn't matter, as long as they match, I can combine these two radicals underneath one radical. It'll be a little bit taller because it's a fraction, but it can be the nth root of a divided by b. And this is going to help us simplify a lot. We'll see that in just a second. So as long as I have the same index when I'm dividing, I can just divide my radicands. So let's take a look at a very simple example of this situation as well. Let's say I have the third root of 6, that's the cube root of 6, divided by the cube root of 2. If I have this situation happening and I have the same root on top and bottom, 3 and 3, then I can combine them under one giant radical and do the third root of 6 divided by 2. And that's helpful because I can simplify what's inside my radical now. I can simplify my numbers by actually dividing them and then check to see if anything can be taken out of my radical. So in this case, 6 divided by 2 is 3. So I would end up with the third root of the number 3. 3 is a prime number. It doesn't have any factors that repeat 3 times, so this would be my final answer. So with that basic principle in mind, let's go ahead and have a look at some examples. Our first example, example A in your notes. Remember, this is going to be on your notebook quiz. Example A in your notes is square root of 45 x to the 5th y cubed. That's our first radical. And I'm going to multiply that by the square root of 35 x y to the 4th. Now both of these are the second root. It's an invisible index of 2. So because they match, I can combine these under one radical. So I'm going to go ahead and do that down here. This is the root of 45 times 35. And I'm going to go ahead and combine my terms one at a time. So I've combined my coefficients. I'm going to go ahead and combine my x's. I'm just going to write them side by side. X to the 5th times x. And then y cubed times y to the 4th. It's going to help me keep everything organized. So I'm going to put my coefficients together, my x's together, and my y's together. What I recommend for you guys is not to combine your coefficients because we're going to have to factor those to separate them anyway. But I do recommend that you combine your variables because the easiest way to simplify those is to break the most simplified version of that variable into the groups that you're going to need to remove it from your radical. So I'm going to rewrite this one more time. I'm going to combine my variables, but not my coefficients. 45 times 35. And then over here, this will become x to the 6th, because I have x to the 5th times x. And then we'll have y to the 7th, y to the 3rd times y to the 4th. So this is considered combined. Now I just have to simplify it. So let's go ahead and take a look at simplifying my coefficients. 45 is 9 times 5. 35 is 7 times 5. Now what I notice here is that 9 is a perfect square. I can take the square root of that. I know it's 3 times 3, so I'm going to be able to remove those 3's because I have a pair of them. I also have 2 5's right here, so I'm going to be able to remove those as well. I'm not going to be able to take out the 7, but that's fine. So keeping them unmultiplied makes it easier to find their factors. If I had multiplied those together, I would have had to factor a very large number that has factors 45 and 35, so I might as well just keep them separated. Now I'm going to go ahead and use the trick we learned yesterday to break down my x and my y. I'm going to take this x to the 6th. I know I have to take the second root, so I'm going to take the exponent 6 and split it into 2 groups using division. It's going to have 2 groups. Each one will have the third power in it, and I have a remainder of 0, so I'm not going to have any leftover x's. So let's go ahead and do the y's now, and I'll rewrite this in just a second. So for our y's, we have y to the 7th power. When I break those 7 y's into 2 groups, each group will have y to the 3rd power. Except this time, 3 times 2 is only 6, which means I'm going to have 1 y left over. So I've just conceptually divided my variables. I'm going to go ahead and rewrite them divided, and this time I'm going to actually go ahead and take my coefficients out, the ones that are possible to take out. So I have 2 3's here. I'm going to take a 3 to the front. I also have 2 5's here, so I'm going to go ahead and move a 5 to the front and rewrite my radical, the square root. My 7 here is still inside, and I'm going to go ahead and break up my x and my y according to the division I did. So my x to the 6th has been split into 2 groups, x, and each x is to the 3rd power, x cubed and x cubed. So we can see that we still have 6 x's being multiplied together here, but they're in 2 separate groups, which is great. Then we're going to look at my y's. I had 7 y's. I split them into 2 groups, y, and y. Each one is to the third power, 3 and 3. And then I had one y left over. So now we can see that altogether, y cubed, and y, that's 7 y's, but I split them into two main groups. All we have to do now is finish simplifying these variables. So I have two x cubes here, so one of them can come to the front. I have two y cubes, one of those can come to the front. And inside my radical, I still have my 7 from here and my y from the end. And then I do have my 3 and 15 from before, 3 and 5 rather, that makes the number 15. If we want to be absolutely certain that we won't have any problem with signs, we just took the second root, and when we took the second root, we ended up with x and y to an odd power. So I can go ahead and put those in an absolute value to make sure that they won't give me any signs that I'm not looking for. And that's it. That's that one simplified. Let's go ahead and take a look at one more example. This example has the cube root of 45, there's that number again, x to the 8th, and I'm going to divide that by the cube root of 5x squared. So because I have the same cube root over the numerator and the denominator, the same index of 3, I can go ahead and combine those under one giant cube root like this. And inside I have 45x to the 8th divided by 5x squared. Now I can actually simplify the fraction inside of this radical. 45 and 5 have a GCF of 5. 45 divided by 5 is 9. 5 divided by itself is a 1. X squared and x to the 8th have a GCF of x squared. So x to the 8th divided by x squared is x to the 6th. I would have 6 left over. And x squared divided by itself is 1. So now all we really have is a denominator of 1. We can make that denominator go away. All I really have is the cube root of what was left in the numerator, which was a 9 and an x to the 6th. Now we can go ahead and see if that can simplify. And it can. Let's see how. The factors of 9 are 3 and 3, and then both of those 3's are prime numbers, so that can't break down anymore. And unfortunately, we are trying to do the cube root, so I'm not going to be able to remove the 9 from the radical. That's fine. But I do have x to the 6th over here, so let's go ahead and divide that into groups. If I have x to the 6th power, I need to divide it into 3 groups in order to get it out of the radical. And if I actually divide 6 by 3, each group will have 2 x's in it, and I will have a remainder of 0, so no x's left over. That means my radical will look like this. It will have the 9, and it will have the 3 groups of x, x times x times x, and each group will have x squared, 2, 2, and 2. Now we can see I have all 6 of my x's. They're separated out into 3 groups, and that's exactly what I need to take it out of my radical, 3 groups. So we can go ahead and bring out the x squared, and the third root of 9 will still be left over. And that's it. We've simplified that one as well. So by combining our radicals, it became much easier to actually remove things from our radical. All right. The last thing we have to talk about is the other form of simplifying, which is rationalizing the denominator. So rationalizing the denominator, remember, means that we cannot have any radicals left in the denominator after we've simplified. So if we simplify our radicals and combine them, products or quotients, and we find out that we still have a square root, cube root, any sort of root in the denominator, we are going to have to do one more step, and that step is to multiply the top and bottom by whatever the radical is from the denominator. That's it. And everything will simplify and we'll have no more radicals left in the bottom. Let's go ahead and try an example of this. So the first example of rationalizing the denominator is going to be 5 times the square root of 7x divided by 5x. Oh, I'm sorry, the square root of 5x. So what we can do is simplify this as much as we can first, and then we can work to remove the radical left in the denominator. So how I would simplify these is to go ahead and combine my radicals. Now, not everything in this function is under a radical, so I'm going to break it up. I'm going to keep the 5 separate by itself. Technically, it's in the numerator, so it's over its own little invisible 1. And we have the square root of 7x and the square root of 5x that are next to it. You can see if I multiply these back together, the 5 and the 7x would stay in the numerator, and the 5x and the invisible 1 would stay in the denominator. So I haven't really changed the proportions of this equation. All I've done is rewrite it so that I can see that I have a matching radical in the numerator, the same index here, an invisible 2 in the numerator, and an invisible 2 in the denominator. So I can actually combine these radicals. And if I do, I end up with 5 times giant tall square root of 7x over 5x. Now combining these is helpful because these x's will both cancel and be replaced by invisible 1's. And all I'm left with is 5 times the radical of 7 over 5. Unfortunately, nothing can happen with the 7 over 5 though. So what I can do here is go ahead and separate those back out again. 5 and the square root of 7 on top, and that square root of 5 on the bottom. And I can multiply it by the 5 by just extending this denominator here. So even after simplifying, we still have the square root of 5 in the denominator, and I can't have that, which means I can go ahead and get rid of it by doing the step on this side, multiplying the top and bottom by whatever radical is in my denominator. So I'm going to multiply the top and bottom by the radical from the denominator, by the square root of 5. And that's it. Once I simplify this, I will have no more radicals in my denominator. Let's check that out. The numerator will have 5, and the square root, and remember, these are both square roots. I can combine these. So the square root of 7 times 5. And the denominator will have the square root of 5 times 5. Now, I didn't distribute these because we will want to try to simplify these radicals if we can. And in the denominator, I'm taking the second root, and I have 2 5's, which means that 5 can come out of the radical. In the numerator, I have 5 times the square root of 7 times 5. Both of these are prime number. I can't make them any smaller, and they don't match, which means I'm not going to be able to remove those to the radical, so I can go ahead and just rewrite those as 7 times 5, which is 35. Now the last thing I'll be able to do with this problem to simplify it is cancel out the 5's that I have in front, which means my final answer is the square root of 35, and I have no radicals in the denominator, which is awesome. It is a good idea to try and simplify your radicals first. If this step is a little bit too confusing, separating it into numerators and denominators and then simplifying and then breaking it up again, you can go ahead and do the same work right from here and multiply the top and bottom by the square root of 5x to rationalize it and then simplify from there, and you should get the exact same answer. There are lots of different ways to get the same answer in these problems. Let's go ahead and try another example. Here's example B. For example B, I've got the square root of 15x squared divided by the square root of 120. Just kidding. We're going to try that one again. I got overexcited, I'm sorry. So we're going to do this one again. We're going to have the square root of 5x squared. And in the denominator, we're going to have the square root of 20. That's much better, much prettier numbers. 20x cubed. Okay, that looks much nicer than we had it before. All right. So first and foremost, it is a good idea to try simplifying first. And if I simplify these are both square roots. So I'm going to be able to combine them under one giant radical, one giant square root. 5x squared divided by 20x cubed. So let's do some simplifying here. 5 and 20 have a GCF of 5. 5 goes into itself once. 5 goes into 24 times. X squared and x cubed have a GCF of x squared. X squared goes into itself once, and x cubed divided by x squared is just x. There we go. Now what we're going to do is rewrite this radical in its more simplified form. The numerator of this radical is just the number 1. The denominator is 4x. So we have 1 over 4x. Now, just like we can combine radicals, just like we saw in the last example, we can also separate them again. So this actually is the square root of 1, just that numerator, divided by the square root of 4x. All right. So in this case, the square root of 1 is just 1. And in the denominator, 4 is the product of 2 times 2, and since this is a square root, I can take this 2 out of the square root sign. So 1 over 2 times the square root of x. And then we're kind of stuck. There's really no more simplifying I can do here, but we still have this radical in the denominator. So all I have to do to finish simplifying this problem is multiply both the top and bottom by the square root of x. That's the only radical I have in the denominator, so that's all I have to multiply the top and bottom by. Let's go ahead and see how that simplifies. My numerator will become just 1 times the square root of x, which is the square root of x, and my denominator will be 2 times the square root of x times x. And since this is the second root, and I have 2 x's here, I'm going to be able to take them out of the radical. So the numerator will stay the square root of x, and the denominator will be 2 times x. And that's it. That's completely rationalized, and we're done.